Start recording. Morning, morning, morning. So I see that there are people watching this for some reason. I'm grateful for it. There are some people who liked it, some who didn't, but this intention was just to be for myself, still grateful. Alright, I'm gonna go to this 5.3, modeling domain behaviors around data. When we think about behaviors in our system or in a system, it usually evokes image of doing or action. Something fleeting and ephemeral that causes change somewhere in the world. The void method. Data orientation takes a more mechanical view of the world. Behaviors are discrete, they change one state into another. Inputs produce outputs. This is a pretty normal way of thinking about or thinking for many parts of our program. ToString is a good example. It's very mechanical. It's a very mechanical operation. It takes in an object on one side and produce a string on the other side. A data-oriented view is to keep up this mechanical inputs and outputs vantage point, even as the operation and states change or state changes become more complex. This includes an ephemeral action like calling an API. We can model that call as two discrete states, the one before the call and the one after the call. What are these states? They are data we have to invent. So these states are data we have to invent. Somewhere in our requirements is a machine that we can model like a factory. Raw invoices come in. On one side, late fees go out on the other side. The design process is figuring out how many of these little machines we need and what each one processes. It's not that different from modeling we did in previous chapters. The only big change is that rather than focusing on a piece of data in isolation, we focus on how pairs of data transform from one to another. Also, like before, we'll ignore the implementation details for now. We're going to invent a lot of new data types as we go, but only in name. We'll ignore what's inside of them for now. The goal is to stay above the implementation details so we can use loose and so that we can stay loose and flexible while we're designing. We can conjure up a new data type out of thin air and then scratch it out just as easily if we realize it's no good. Telling story with data. We know the inputs to our system. The invoice is already made for us. What we need is the output. So let's start there. We can give ourselves what we know is already missing. A data type called late fee. This type is the whole reason our service exists. Our factory takes a list of invoices as input and produce a late fee as output, which will eventually cause a new invoice to be added to the state of the system. We'll represent this jump from one data type to another by drawing an arrow between them. What does that arrow do? How is it implemented? It doesn't matter. We'll figure it out later. The important part is the relationship that this magical arrow creates between the input data and the output data. When we put them next to each other, they should tell us a story. So A list of invoice produces late fee invoices. Okay. We read this as saying we start with a list of invoices and then use those to produce a late fee invoice. Just like with the arrow itself, we won't worry about what these data types are. Is a late fee invoice related to an invoice, part of a hierarchy or sealed family of classes? It doesn't matter at this point. They're semantically different. And that's what we're trying to capture. We're dealing with how we'll deal with how they're implemented later. These transformations between data types form the basic building blocks of our story. They're how we communicate the core ideas in our domain. So each time we add a new pair of data types, we should pause to see what kind of story they're telling, if that story is the right one. If you imagine describing this feature to a coworker, you'd probably notice that the current story, invoices are used to make late fees, miss a lot of subtlety. It's not any invoice, it's specifically past due invoices that produce late fees. The state of the invoice is important. That's why we're charging fees in the first place. We can clarify the story by adding another step with a more descriptive data type. So, late fees. All right. A list of invoices is used to make a list of past invoices, and those list of past invoices are used to create late fees. What's cool about playing around with data types like this is how quickly the story comes to life. We're able to communicate the core ideas in the requirement without writing a single line of code, implementation code. Let's keep fleshing out this story. One of the core subtleties in our system is that the fee invoice we make isn't real until we submit it to a billing system. What we are really doing at this stage is creating a description of invoice that we want to have later. We can think of it as a special part of the life cycle. It starts out in our system as a draft, then reaches its official invoice state of open once it is sent through this billing system. Interesting. Life cycles like this pop up everywhere in programming. They're not part of the real domain, but exist as a consequence of the software system in which they live. Invoices officially only have two states, open and closed. Okay, it's important to capture them. Let's refer to our pipeline to make the life cycle to make that life cycle state explicit. Note here that refactor just means slotting in new data types. This ease of shuffling things around is why we stay up above the implementation details. It massively lowers the cost of iteration while we design. So, what do? We start with a list of invoices, then we make use of that to produce a list of past use, and then we use that input to produce an output of late fee draft. And after that, we use late fee draft to produce a list of late fees. So what is a late fee draft? Capturing the fact that in our domain, past due invoices are used to create late fee drafts. This is beginning to capture something interesting. If you mentally replace each arrow with with a phrase like, and then we use that to make, you'd end up with something that really does begin to read like a simple story about our requirement. So use this. Under this light, you might notice that our story is still missing a bit. It says drafts become invoices, but in reality, only some drafts will go on to become late fee invoices some of the time. The why and when are the most complicated part of our requirements, and also the most complicated part of our original implementation. If you remember, we do a check if it's less than or equal to 0. We just don't bother to send it. If it's greater than 1, I have to do like some checks here. The check if the customer that get approval ID is empty, then you do some logic. Else, if it's pending, you do additional logic. Else, if it's denied, do another logic. So we have trees. We have about 1, 2, 3, 4 non-billable, non-billable, and somewhat billable, I guess, and say that's 2 categories, and one of them has different states. So I think if it's greater, you check is empty. There is a state where you just don't, you get denied of billing people, I guess. Don't know. Inside of that wall of nested if-else condition sits a really simple idea in our domain, deciding what to do with the draft. It's either billable or needs manual approval, or below the threshold where we wouldn't bother the customer. It's just hard to see those 3 discrete decisions because the code is forced to juggle so many other concerns. But these decisions are the important stuff. It's what we want the people who read our code to understand. To do that, we have to lift it out of the implementation and capture it as data, representing runtime decisions as compile time algebraic types. And I guess that's what you had to do at the end, algebraic data types. So this is important. So hence why we have this implementation. I find this implementation a little odd, right? So you can non-billable is when you just don't give a crap about it. So you just, I can say non-billable, and if it's a billable, you have to check if it's over the threshold, within the threshold. Right, that's what I was thinking about. So you check over the threshold. Within the threshold will be I don't know. Over the threshold. Sorry, unbillable. Oh yeah, over the threshold would be this guy. And I was thinking, well, billable is something that has to be over the threshold, right? You have to be greater than 0, and in that you have this logic, that logic, and that. Any decision we make using if-else statements at runtime can be expressed algebraically at compile time as data. So we have our example: if option 1, else if option 2, else option 3. When we represent those options, we have 1, 2, and 3. It's just an example. And they are now data, so we kind of do an if else on it. you know what I mean? So it's like, that is what I think is happening here, because you're just switching on it. Switches, I don't know, but I think this is still, you're still doing an if else statement just on data, saying if is this data, do it's this, check if one of, it's one of this data. That's all you're doing. So this modeling approach has powerful implication because it decouples where we make a decision from where we act on them. Conditional expressions are almost always paired with their associated actions. Okay? So some condition, do something else some. However, if we return the decision itself as data, we get to defer the action part till later, if at all. We can build custom interpreters for those decisions and decide how and where we want to handle them. So you do an if else. You do an if else on the data, because this have to return, right? They wouldn't just disappear. You get a condition. Hey, we're going to do something on this condition, right? We're going to check the option 1, which is a condition. If it's option 1, return this, or return that, or return whatever. So, yeah, feels to me like an if statement. This buys us a ton of modeling flexibility. Most importantly, it allows, man, I'm tired, bro. It allows us to lift an otherwise hidden part of our domain up to the top where everyone can see it. So we do all this, becomes a draft, then we say, okay, it's either billable fee or not billable fee or needs an approval. I think if you have it within the threshold, then you decide if it's billable or not billable. You know what I mean? Let's see. Yeah, then you decide if it's billable or not, depending on how you see it. But lurking in the background are more life cycle states. If you carefully study the billing API way back in listing 5.1, you'll notice that we are not guaranteed to get back an invoice. The service can decide our late fee isn't billable. So our story doesn't conclude with the production of a singular late fee. It ends with a late fee in a particular state, one that's either billed or not. That's the hard part done. The rest of the process follows the same pattern. We match invented inputs to invented outputs and keep refining the story until we've got a simple map of how data flows through the program. That's nice. So we have this. Take a minute to notice how different this feels as a starting point. You can see our requirements directly in the data types. We don't even need the implementation. The data type tells us a story. I agree with that part. I am just literally confused at this part. You're just doing an if statement, innit? Yeah, I get. Make your data clear. I'm with you on that. The other semantic craziness is this one. Because if you decide to build it, this is what you get. Yeah, I have to, maybe it's an IDE issue, text editor issue, but let's say you have these things that are nested, right? Because, yeah, you can say, okay, we'll have this, but we know that we have things that are billable, and we know that we have things that are non-billable, at which point we don't send anything. But even for the billable types, you have different over the threshold, within the threshold, and even that, right? It depends on, I guess, to his point, it depends on how you intend this to go, right? So yeah, but 100% with him on data should mean something, but in companies, and with the advent of sprint or agile, agility, scrum, whatever, you don't have time to do this, especially if you're a junior developer. You have to just push through code. And as a senior, you have to have grace and have the wherewithal to say to the agilist, hey, we have to make this pristine so that the next people will not fall into the trap that we did, right? That is important. But you don't only have to talk to the agilist, right? You have a deadline. Products have to ship. Whether they're good or not, nobody cares. Because, well, it should be good, should not break, but to what standard, right? If you can't, you get fired. So this is an ideal world, and I'm probably sure he states that in the beginning, right? Like, you just write shitty code sometimes, man. Yeah, I guess. Okay, let's continue. I like it though so far. Playing around with data like this is a powerful design tool. It helps us to refactor and refine this pipeline endlessly at no cost because we haven't committed to anything. We don't even know what these data types will ultimately look like. The process takes many pages to describe in a book, but only a few minutes of effort in real life. Designing behavior with this way lets you rapidly explore different approaches and step sizes. True. It lets you build up a high level story of how the data transforms as it moves around in our system. So, when are we done? That answer will vary from person to person. The endpoint I shoot for is to keep refining until I end up with baby code. That's what he calls it. I wanted to read it like a set of instructions, written for a human rather than a computer. Done is when I can see all of the major requirements as a narrative. So he wants to see it this way. First step, collect the past due. And how do you do it? From a list or an input of invoices that are lists. use those to build the draft. You take the past use and it becomes an input to create a late fee draft. Then you take those late fee drafts that are of this type, I guess, decision, right? And you use them to create this, I guess. Oh yeah, so you take the past draft to create this, and you take the billable or whatever to create whether it's this billable late fee or rejected late fee. And then you have one that needs approval, which then starts a new state. The approval started state, and then it's ultimately either not billable as well. So it's this state or this state. All right. Once you're happy with it, you can take each step and turn it into a method. A method. When you say a method, you mean it can mutate? And so you're mutating data at this point, I guess. Because a method in Java just means mutation, right? Identity objects. Inputs feed outputs. Outputs feed the next set of inputs. This becomes a high-level guide to our implementation. These transformations together make up what our behavior is. Of course, these won't work yet. They're just a rough sketch. They're missing all the other stuff in our domain that comes from external services calls and repositories. They're here as a high-level guide for our implementation, so let's flesh this thing out, baby. Fleshing out the representation. We have to decide how we'll represent the data we invent in our sketch. This puts us back in a familiar territory of modeling individual nouns. However, the real world brings challenges to the modeling process that weren't present in previous chapters. Well, let me tell you, man, naming things is hard. And I think for me, I'd say it's hard because it's gonna be really, really hard if you start a career, because you have to juggle with understanding what the requirements are. If you understand the requirements, you have to ask yourself some questions like, do I want to make this very specific, or do I want to open the window of making it generic to have the openness to capture a lot of things? And you don't want it to be too specific, and you don't want it to be too generic or general. And sometimes you don't even want it to be in the middle, right? So you're gonna find out. You know what I mean? So it's a hard thing, because you may think that you're making sense, but you're making sense to you now. The only way you get confirmation that what you're thinking and putting into code makes sense is when you do a pull request and people are able to understand what you're talking about, right? Or understand what your code is talking about. And not only that, is also when people start using your tool, or the programmers start using your tool. Are they writing comments everywhere? Do they understand stuff, So yeah, it's hard. Naming is hard. In addition to making sure that data types are self-describing and semantically clear, we also have to ensure that their semantics fit the behavior we've designed. Each time we tweak our data's representation, we have to take a step back and check out how those choices have rippled outwards through the system. Good representation removes bad states and potential bugs. Weak representation creates them. I'll be back. I need water. Yep. Additionally, we have to pay super close attention to the ergonomics of the data types we're creating. Clear semantics are great, but if getting those semantics into our code is painful and awkward, most developers won't put up with that annoyance. We have to ensure that clarity doesn't get in the way of our quality of life. Excuse me. These challenges mean that we won't always get it right on our first try. Design is an iterative and messy process. The first solution we come up with is just that, the first one. There will be many. Design is the exploration of those possible solutions. The more time we spend exploring, the better the odds we'll find the right trade-offs. So, we have some complicated modeling decisions to make. We introduced several new data types in section 2.3. Our representation of these data types and how we relate them together will have a massive influence on how our code feels and the kinds of invariants we can enforce. The state of invoices that are relevant to our feature past due, okay? Decisions our application makes about what to do with late fees. Either billable, non-billable, needs an approval, different lifecycle states of a late fee. Section 4.1, creating a wrapper type, creating wrapper types and being okay with commingled identities. That's a funny subtitle, bro. We'll start simple with the past due data types. It stands out from the rest because it's purely informational. It doesn't track any unique state or have any novel attributes of its own. Past due represents something we know about the state of an invoice entity. They are literally past due. Alright, I think the code part is coming. Alright, let's see what's here. We'll have So where are we putting past due, man? Are we putting past due here? Past due. Okay. Let's do this. How about we take, I'm gonna I don't know. Well, all right, so let's create a record, call it past due. It's gonna take a list. Why is it taking invoice? Just one invoice. I don't get it. Invoice. All right. Right there. Let's go here. Actually, a record. I'm gonna call it past due. And take an invoice. Cool. All right. Once we have a new data type, we can ask ourselves questions about semantics. And that leads us to one of the unfortunate realities of building on top of what's already there. Invoice is a mutable identity class. Correct. Not a value. So even though we want to design and program with data, we're getting dragged back down into the wall of identities and change. That is fine. We got him to tell us what to do. In situations like this, where we're bridging the gap between the way we used to do things, mutable entities, and how we're starting to do things, programming with data, there's going to be some unavoidable mismatching, and that's okay. Data orientation is not about purity. What we want is clarity. All of our modeling is a pursuit of that goal of getting more clear. Immutable data types make that goal a bit easier to reach, but it can still be achieved even if we bend or break the rules from time to time. Yeah, man, I'm with this. Of course, we could also fix this problem. We could make an immutable version of invoices or model past due so that it can hold immutable copies of the relevant data types rather than just wrapping the immutable object and the immutable object identity. But we also don't have to do that. We can always redraw those boundaries later. For now, wrapping can be enough. In fact, it acts as a quarantine for the invoice's mutability. Does it? So you take a class, and you know what a class is. You can do a lot of things to a class, mate. For now, wrapping can be enough. It acts as a quarantine for the invoice's mutability. In order to modify the invoice in place, you'd have to ignore the spirit of what records are supposed to be and actively abuse their shallow immutability. Actively abuse their shallow immutability. That's bad, bro. That's a wicked statement. All right, let's abuse it then. Okay. This one-line rapper has some more problems in store for us. If we ask our familiar model in question, what does it mean to be past due, we'll get a complex answer that depends on different requirements, many of which involve the state of the world and things outside of the scope of individual invoices. Okay. These are very different kinds of constraint from the ones we explored in previous modeling exercises. Data types like non-negative ints and degrees are self-contained. Everything we need to enforce their semantics is available right in their constructors. Cool. Past due is a very different kind of data type. The meaning of past due is contextual and depends on outside information. Right. So, if you're checking it and you're saying if invoices dot date due dot is before, we're gonna give it something, right? Then you want to do something with it, right? So we're already defending. In the ideal world, we want data types that got their own meaning and prevents us from making mistakes. But past due cannot do that as designed. Something can only be past due relative to other dates. Of course, we could redesign the types to track that state. Right. Okay, and what's that? The redesign of that is that's interesting. Okay, the redesign of that is to say, well, so you have this local date late as of, right, and then here you're still defending, right? Is that what we don't want? We don't want defending. And do if invoice dot due date dot is before, I think it's due date dot is, wait, what is going on here? Right. Actually, I think it has to be past due. Right. If invoice dot due date dot is before, correct. It is, right. Cool. it's before that time, and is a standard invoice and is open and blah blah blah. So you're doing all this, but should we? It really depends. I'll get stressed that the goal of data orientation is not. I'll again stress that the goal of data orientation is not purity. We want clarity of communication. We want code. We understand data types are a means to an end. So, what will we do? So, there's not really a right answer here. It can be useful to take a step back and remember why we added these types to our design in the first place. It's there to give a name to something that otherwise be implicit or forgotten as soon as we leave the bounds of the method that computed it. Okay? A draft that says it's built from past invoices communicates something very different from one that says it's built from any invoice. Right? So we need something that communicates that. Now, we have this methods. Let's say we have this method. These are all, what the hell dancing monkey is this? Alright, so let's do public. For now, let's say void, because we don't have that type yet. Or should I say, actually, let's change inside this. Let's say create late fee draft. It's gonna be a list of invoices. Right, and actually let's do this. Create a list. Yeah, has to. So if we go back to this, that's how code goes, right? Let's go back to late fee draft. Yeah. Okay. What different inputs communicate? So this creates, yeah, so I think this is the right one, I guess. Right. Okay, late fee draft. Let's yank this word. Record. Well, not that. Fee draft. All right. Given that, sticking with a bare bones one-line wrapper type, I don't know if this mic is hot or not? So a hot mic, still a hot mic. All right. Given that, sticking with a bare bones one line wrapper type, even with all of its shortcomings and semantic imperfections, seems like a good option to me. It conveys something useful to the reader, and that's enough to make it valuable. Um, this is the design process. We are constantly weighing different, often competing concerns. We have to balance between expressivity, power, correctness, and semantics. Designing the algebra for late fees. Alright, oh, what is this? Oh, yeah, that's my intentions for the future. To understand what you're using, it's important. Let's say, okay, designing this. Yeah, I guess. The remaining data types pose an interesting modeling challenge in Java. So you have a draft, approval started, build, and rejected are data types that represent the life cycle of a late fee. What makes it tricky is what is how similar these types are. Each type only differs by one or two attributes. They share everything else. Okay, so you have a draft, let's say late fee. These are the same across all of our data types. String custom ID, US dollars, charges, invoice date, past due date, and then you produce a list of past dues included in fee. This plus invoice ID is equal would create a build late fee. This thing over here plus reason rejected late fee. This plus approval equals approval started. This plus nothing. So just this alone is just a draft. That's how I read that. May be wrong. Records are great, but by design, they don't allow extension. We can't inherit between data types or derive new data types from existing ones. So we have exactly two options. One, duplicate the fields we need, or B, create wrappers. And you know what developers do? They wrap it up. You just wrap it up. Wrapper on a wrapper about that wrapper that is a wrapper to another wrapper that is actually a wrapper to another fucking service. That's what we do. Please don't make it that way. Okay. Let's see. The first thing we might try to start with this. The first thing we might try to start with the simplest and obvious approach. We could design each type such that all of the attributes are duplicated between them. So you have that. And then you have build, and then you have this. I'd say you have a base, right? Say you have a base. Let's say the draft is the base. And then you get that. And then you get that. So the base is just going to be a wrapper for draft. You know what I mean? Most developers will somewhat appropriately have a visceral reaction to duplication like this, like I did. We are competing with the free, usually supplied by our frameworks. I don't know what that means. We are competing with the free, usually supplied by our frameworks and ORMs. Slapping nullable fields onto an existing entity is easier than maintaining this duplication. Comfort generally beats out semantics. Yeah, like if we have, I don't know, what am I thinking? Let's say we have this. Let's say we have a record. Let's say we have a record A, right? And you have what? 1, 2, 3. Right? Let's say we have a record B. B of A. Right? And then you have a record C of A. And then you have a record D of A. Right? And here you'll have A. Right? And here you'll have A as well. Right? Maybe A has like what is it called? A string, whatever. Just A or CI, and this has a string of DI, like that, right? Because that's the main change, right? A string, even that feels slimy, of BI, something like that. Why is that? All right, so you have an object, right? That's what I'm thinking, but maybe wrong. Okay, most developers will somewhat appropriately have a visceral reaction to duplication like this. We're competing with the free usually supplied by our frameworks and ORMs. Slapping nullable fields onto an existing entity is easier than maintaining this duplication. Comfort generally beats semantics. But before we dismiss this for not being dry enough, let's look at what it enables. These data types are clunky in isolation, but expressive in the broader program. They make it possible to enforce semantic invariance. Review draft, assert draft, assess draft. Okay, it takes a draft fee. Right? They are what enables us to tell a story with just data types. But isn't draft just the base for all of them, the way I see it? Okay, revisiting the narrative of our feature, we start with a list of invoices which is used to produce a list of past dues, and that is used to produce a draft late fee. Draft late fees is used to produce whether something is billable, and that billable can be billed late fee or rejected late fee. And we have that in which needs approval. Alright, however, they remain riddled with duplications, and that won't do. We have to figure out how to get the semantic clarity without any of the copy and pasting. So, as a next step, we might try extracting the duplicate code into its own data type so we can reuse in all our models. Yeah, that makes sense to me. right? Let's have what I did, right? It's basically what I did. He's talking about what I did. That's cool. Yeah. So you're gonna have something like this, you know. Gonna have a base. Let's call this a base, you know. Whatever that is, right? And this will be the base. It's all about the base, right? All about the base, man. All about the base. And then you have a string. BOA, whatever that entails to you, you know. But yeah, not my cup of tea. Yeah. All right. We have that. Void. Let's call this void for now. All right. Yeah. Let's give that a shot and see how it feels. So you create something called a base. This approach looks pretty clean. So record details, right? So this is a record detail. Yeah, that makes past due. I don't know. Past due all of a sudden. I don't know. I think I'm really tired and I need to stop now. If not, it's gonna be just crappy all the way through.